Welcome back to ECE 442-542. If you are doing the online, make sure you understand which way you are going to take your exams, either through Examity or through a proctor, or some of you have actually said you wanted to come on campus to take your exams. If you're taking it, just make sure it's clear, or you let me know so that I can have some extra exams available. If you're taking your exam via Examity and you've never done that before, I've listed some resources or provided some files in the course resources module on D2L for you to look at. Hopefully that will then clear everything up relative to taking an exam using Examity. Reading assignments, we're still doing the Z-transform, and now we're going to be talking about region of convergence, and we're in Unit 2 now. Somebody was saying I didn't see the video posted, but it's now, we're in Unit 2, which is the Z-transform section. Obviously, if they didn't see the video, you won't hear my advertisement for that video watching this video, since you won't be able to find this video, but I've tried to now make it clear via some emails to students that we're now in Unit 2 in the course, and that will then mean that homework number 2 is due in a week, not Monday, but in a week, and our exam number 2, our second exam, what did you think of the first exam? The first exam is scheduled in 2 weeks from today, and we will have a review session at 7 o'clock next Wednesday after class. So we'll have our normal class, and then we'll do a marathon session. We will go until about 11 p.m. No. But we'll look for a review session at 7 p.m. I do have this room reserved, so that's where it will be. If you have questions that you would like addressed during the review session, there is a quiz in D2L. You should be able to just write down or type in or upload a scanned question into that quiz. You don't have to take the quiz unless you have a question, but that's where I'm receiving input for possible questions for the exam number 1 review session. Today what we want to do is talk about properties of the Z-transform, and then we will get into looking at the frequency response for a discrete time system. Hopefully you remember something about a frequency response for an analog system or continuous time, a Bode plot. Well, how do we find magnitude and phase information associated with a transfer function for a discrete time system? Hopefully that will become clear as we go through that, and we're actually going to try to make the connection with what you already know. Let's start with a low-pass filter. If you're in electrical and computer engineering, that should be clear. If you're not, I think it's straightforward enough that you will be able to understand it if you're coming from a different major or from a different perspective. In discussing or talking about properties of the Z-transform, here is what we will be using. The definition of the Z-transform, and the notation is capital X of Z is then defined to be script Z of this sequence X of N. The first property is referred to as linearity. If you now combine algebraically with a sum or a difference and you scale 2 sequences, then you can actually, if you know the individual sequences Z-transforms, you can essentially scale and combine their Z-transforms to find the result. What you'll want to make clear, though, is that in fact the region of convergence may change when you start combining Z-transforms. meaning you might have one region of convergence for f sub 1, another region of convergence for f sub 2. You combine them, now you have to figure out, okay, what is the actual region of convergence? Sometimes it may reduce in size, sometimes it actually may get larger, the region of convergence. Let's look at some examples, and as we're doing that, maybe we can sort of use this as a little bit of a review. Suppose, so now we're talking about how does the region of convergence change when we combine two sequences. And in this example, this is a special example. Let's look at one sequence, f sub 1 being u of n, and in this case I want that u of n to be the unit step. And u sub 2 is now u of n minus 1. That likewise is the unit step. It's just been delayed. So this is a delayed unit step. Here I'm going to do a straightforward combination, but here I'm going to actually subtract. I'm not going to change the weighting on F1 and F2 with any alphas, but I do want to compare them. And now I hope you can sort of see what happens when you compare f sub 1 of n with f sub 2 of n, or subtract f sub 2 with f sub 1. Now, in fact, you're saying something like u of n, well, you are saying u of n minus u of n minus 1. And what does that actually produce? You now have 1, 1, 1, 1, but you take away a shifted version of that same sequence, 1, 1, 1. You're only left with ONE, one non-zero value, and it's located at the origin. So this, if we, I don't know, did we use this notation before? The result is in fact just the unit pulse. And that unit pulse has a different region of convergence than either F1 or F2. Meaning, suppose we now, what is the region of convergence associated with F sub 1? And we'll call that ROC1. Or let's just find capital F sub 1 of z. I only need to worry about the indices from 0 to infinity, since the unit step is only non-zero over that interval of time. Or maybe I'll just put some more steps in here. This is now what I'm doing. Where this is now my sequence, and it's only assuming one value, and it's the same value at each instant of time n. And if you now looked at f sub 1 of z, in terms of its series, it's now 1 plus z to the minus 1 plus z to the minus 1 squared. I'm writing it in a way to explicitly illustrate the common ratio, which we can now use to modify the original series given by capital F sub 1 of z, and now we have Are we following along what we're doing? Such that if we now compare those, or subtract the bottom row from the top row, we end up with 1 minus z to the minus 1 f sub 1 of z equaling 1. But when do those two series converge? It converges when that common ratio has a magnitude less than 1. Where our common ratio, here's our common ratio, z to the minus 1, that magnitude is less than 1, or it converges now, or we have f sub 1 of z equaling 1 over 1 minus z to the minus 1 as long as z to the minus 1 is less than, the magnitude of z to the minus 1 is less than 1. Or z is outside a disk of radius 1. That's ROC1. Can you distinguish between my vertical bars and my 1? Not very well, can you? But that's 1 is less than the magnitude of z, or z is bigger than 1, the magnitude of z. That gives you this entire complex z-plane except for the unit circle has been removed. That's the region of convergence number 1. What's region of convergence for f sub 2 of n? Or for little u sub n minus 1? If we wanted f sub 2 of z, how would we write that in a summation form? What indices do we need to sum over? Now little n doesn't start at 0, it starts at 1 and goes to infinity. This one now is going n equal 1 to infinity, but the sequence is still the same. Once it starts, it has a value of 1, z to the minus 1. So this is now z to the minus 1 plus z to the minus 2 plus dot 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 plus z to the, whoops, let me say my tail goes on and on. And when is this tail going to be okay? Or when does that series converge? Oh, that 2 doesn't look very good. That was a 2. I looked at it and I thought I had 2z to the minus 1 summed together. It's z to the minus 1 plus z to the minus 2. We have the same common ratio. That has to still remain less than 1. And what is f sub 2? Can we compare that relative to f sub 1 of z? If I now wrote this as z to the minus 1, 1 plus z to the minus 1 plus z to the minus 2, this is now what we were calling f sub 1 of z before. And the region of convergence of 2 is still going to be this z bigger than 1. But what happens now when we combine f sub 1 and f sub 2 in terms of its region of convergence? Did we call that anything? Maybe we didn't. We called it f of n. What's f of z? You can now compute this two different ways because you know the linearity property. You could say, well, that must be f1 of z minus f sub 2 of z. Well, f sub 1 of z was 1 over 1 minus z to the minus 1. F sub 2 of z was z to the minus 1 times 1 over 1 minus z to the minus 1. And do you see now that the numerator and denominator will be the same if you put those two terms over the same common denominator of 1 minus z to the minus 1? Or we now have 1 minus z to the minus 1 over 1 minus z to the minus 1. Or we could have done f of z from the sequence. And what does that look like? That's now f of 0, z to the minus 0, plus f of 1, z to the minus 1. But remember, all of those were 0. And we just had this very first one equal to 1. So that was 1, and we do get consistency here between the different strategies for computing the z transform. But what's the region of convergence for that right-hand side to converge? What values of z does that right-hand side, or the red number 1 is what the result is, what values of z allow that to converge or to be a finite number? All z. So now the region of convergence for this new function, which is a linear combination of two other functions that had different region of convergences, now the region of convergence for f of n is now really just all of c. Z is now an element of C, where C, I'm saying, is this entire z-plane. And what was region of convergence 1?
Where z is greater than 1.
It was the whole thing, except we had a hole cut out, where the hole that we cut out had a radius of 1. What was region of convergence 2?
Same thing.
Same thing. And now when we combine those, our region of convergence has changed. So when you're doing linearity, if somebody needs to ask you about the region of convergence, realize that it might be different from any of the region of convergences of the pieces that you've combined. That's what I'm trying to drive home with this example. Was there a question? Yes.
So why is f of 1 is 0? That's because
F sub 1, oh,
just
f of 1. Why is f of 1 0?
Oh, because never mind, I'm sorry. The only term is f.
So the only term left here in this combination, this particular f of n, if we drew it, ends up only having one non-zero term, and that non-zero term is at n equal to 0 because we're combining those two sequences and they look the same beyond n equal 1, or n equal 1 and beyond, all the way to infinity. To infinity and never mind. Oh, is that copyright? Okay. I'll have to go back and erase that part. No, I'm not going to do that. Hopefully no one will hear it. I don't have anybody watching this anyway. So, yes, question?
Someone pointed out that for the z's, it should be z to the minus 1. So if you scroll down, to the minus n.
Yeah.
I think
Where?
up a little bit. Go up again. They're right
Yeah,
there.
So now what am I doing?
So f of 2 of z should be.
Oh, yes, thank you. So this should be z to the minus n. Thank you for that correction. I get a little sloppy. I know what I want and I know what it is, and I go on like I know, like I'm seeing that it's in.
His idea. I don't want to take credit.
Thank you. So do you want your picture taken, and we'll put it in this video? No one will see it, right? Yeah, so it's yeah, you're copyrighted, your image. Yeah, you're on one of those. Yeah, you're going to profit off of your image just like all the athletes. But that doesn't take effect for a few years, does it? Isn't that coming into, that's a few years away. Darn. All right. But now do you see that was a long road to make sure that it's clear that when you combine sequences, their regions of convergences could change. Let's look at another one. Let's look at a B example. G sub 1, let's say, is 1/2 to the n. G sub 2 is 3/4 to the n. And we want to just add them up. What happens to their regions of, or what is G1's region of convergence? We can find that if we, and if you don't, and if we do this a few times, now all you have to do is kind of quickly pull out a napkin, write this down, and you, oh yeah, now I remember what the region of convergence is. But let's just do it. This is now the Z transform of little g1 of n. That's now this summation, and this is only valid for non-negative little n's. We're summing from n equals 0 to infinity. This is 1/2 to the n, z to the minus n. Yes. That's the definition of the Z transform. And sometimes it's cleaner, I think, to just put these two together. We have 1/2 z to the minus 1 to the n. And now we can see our common ratio. The common ratio is what's inside those brackets or parentheses in our series expansion. We now have capital G1 of z is 1 plus 1/2 z to the minus 1 plus 1/2 z to the minus 1 squared, etc. That's capital G1 of z. And now our common ratio between terms in that series is 1/2 z to the minus 1. And I'm kind of hoping that you remember, well, we don't even really need to know what the expression is, but we would then compare that to the common ratio times capital G1 of z and end up with capital G1 of z equaling 1/1 minus 1/2 z to the minus 1. And when would that be valid? Or when would that have converged? When would that series converge? Now we're wanting our common ratio to be less than 1. Or we now have 1/2 over z, the magnitude less than 1, or z is now outside this disk of radius 1/2. Any z outside of that disk will allow this sequence, this sequence is Z transform to converge, or its series to converge. That's ROC1. What was our second G sub 2? G sub 2 was 3/4 to the n. Do you see what's going to happen here? Now we have G sub 2 of Z is the Z transform of 3/4 to the n, which is now this sum from n equals 0 to infinity of 3/4 to the n Z to the minus n, which is now sum obviously I didn't leave myself enough room. I can cut and paste. Sorry. What's the common ratio? For that series to converge, we need that common ratio magnitude to be less than 1. Or now this says that the magnitude of 3/4 is outside, the magnitude of Z is outside of 3/4 for convergence. This is now region of convergence 2. What are we interested in? We're interested in the region of convergence of little g, which is the combination of G1 and G2. Now we need Z to hold, or for this region of convergence to hold for G. And when will that be true? Or when will both of these regions of convergences be true? So I should have left myself more space, but here we have region of convergence 1, region of convergence 2, that's supposed to be centered at the origin. Please don't hold me to that, but that's a disk that you've drilled this hole out, centered at the origin, and this is now 3/4. This is region of convergence 2. What if we now combine G1 and G2? Oh, I'm stretching this tablet's capabilities, aren't I? Or mine. Probably more so mine. That's why I'm an engineer and not an artist. But what do I now have? If I want both of these, I have to have both valid. What's the condition going to be for my region of convergence for little g? Now it's the intersection of those two, isn't it? It's going to be the area outside of the region or this disk of radius 3/4. That will be the values of C that are true for both cases, because you have G1 and G2 summed. You need Z's to be true for when they're combined. So now you need the region of convergence for little g to be beyond 3/4. So region of convergence for G of n there's the 1/2, there's the 3/4, it's now right there. And in that case, your region of convergence is consistent with one, but not the other of the two that you started with. So it's not always going to be region of convergence getting bigger. Sometimes it will be smaller than one or both of the original sequences that you're combining. So in this case, your region of convergence is actually region of convergence 1 intersected with region of convergence 2. In the first example, case A, the region of convergence actually got bigger, didn't it? Here it's getting smaller because you want it to be true for all values of z when you have little g sub 1 plus little g sub 2. Yes? So now in this case, you couldn't tell it from my sketch, could you? I'm sorry, but this is now the region of convergence. That's what I was meaning for the region of convergence for little g. That's my sketch. It's beyond the pole at 3/4. Wow. That's property 1. Property 2. Okay, property 3. We'll speed this up. So property 2 is convolution. You've seen this before in the analog case. It's now different because we're dealing with, I mean, it's not different. The concept's the same. You have to flip and slide one of the waveforms in the time domain. You're convolving F1 and F2 in the time domain. Now instead of integrating, you're summing, but you're now having this same convolution behavior, and in the frequency domain it corresponds to the product of the two z transforms, one for f sub 1 and one for f sub 2. That's why we like to play with the frequency domain, is now we can have the z transform of our input and we can combine it by multiplying with a transfer function of our system. We don't have to worry so much about convolving in the time domain if we don't want to. We can do a lot of our analysis. We can go into the frequency domain, work with block diagrams, and then if we need the answer, we can inverse Z transform, which will be unit 3. That material will be tested on exam number 2. Exam number 1 is simply unit 1 and unit 2. Property 3, time shift. Here it gets a little interesting, but little n is what I'm using for my time index. That's varying. Little n is marching along. That's my time index, 0, 1, 2. L is a fixed integer. L is 1, or L is 2. Or L is 5. It's whatever fixed integer you need it to be to satisfy this expression. But whatever L is in your function, in your waveform, little f, it's exactly the same in the switch. We are consistent with when we're switching the function on based on how much is it advanced or delayed, and we're consistent with when we're switching that on by the same amount of advance or delay. And in that case, we have nothing left over. We simply have a time-shifted result in the frequency domain, which corresponds to a multiplication by z to the L or z to the minus L if it's an advance or a delay. It gets a little more interesting when we have a mismatch between the delay in our function and when we switch that function on. If we look at this, let's say the blue sequence is representing some f of n, and now if it was delayed by 2, And if the unit step was delayed by 2, then we would just be doing, well, maybe I shouldn't have done that. Suppose we delayed by 2, little l was 2, and now, this is hard to explain with just one curve. I want to shift that and then show when it's on. If I shifted this sequence of blue lines or delayed it by 2, you could shift it over, and now that value at -2 would be right at the origin. And then I switch it on right at the origin, so now I've picked up these values -1 and -2 in this expression that I'm trying to z-transform. Conversely, if I had shifted this by 2 and my switch was on at 2, then those blue lines that are at 0, n equals 0, and n equal 1 would be underneath that yellow switch, and I would basically just be obtaining a shifted sequence consistent with what I was thinking. I wouldn't have any extra terms. So that's the distinction between part A and part B. The window now is at time 0, and my delay is not aligned with that switch. Let's see if we can apply this expression. This now is a different expression. Now, in addition to z to the minus l weighting f of z, do you see that we have additional terms present that could have powers of z associated with them? Just like when you Laplace transform a derivative, you start having these initial condition pieces added on to s, capital F of s, for example. Suppose now we just look at the case where little l is 1. What does the property tell us the right-hand side will look like? If this is now L equal 1. I want you now to use this and put it here. Can you tell me what goes in the yellow box? It's now z to the minus L, and L was 1. Oh, and this is y of z plus, now I have this sum from m equal 1 to L equal 1, f of minus m, z to the m minus, and now that L is 1. Pardon? Oh man, thank you. This should be little y of minus m. I was being too direct on that property, wasn't I? So this is now y of minus m. That's why I picked y to begin with, so you could maybe follow what I was doing, and I'm confusing you even more. But now with the correction, hopefully you're okay. This is now where L goes, and L also goes right there. How does this now reduce or clean up a little bit? Now we're summing from 1 to 1, so it better clean up. We're not going to have too much going on inside that sum. We have z to the minus 1 y of z, which we would have anticipated since we had a delay of 1, and that in the frequency domain corresponds to multiplication by z to the minus 1. That term seems good. Now what do we have? Now we have plus y of minus 1, z to the 1 minus 1, and that now gives us z to the 0. So in fact, we end up with z to the minus 1, y of z, plus y of minus 1. Because of that offset between when we switched it on and when the delay, how much delay we actually had. We had a delay of 1, but we switched it on immediately at n equals 0. And so that y in the sequence at n equal to minus 1 shifted over, and it was on top of n equals 0. And that's now where we're trying to z transform from. What happens if we put in L equal 2? If you were doing partial credit on an exam, how would you get some partial credit? On the equal sign, on the right-hand side of that equal sign, what would be an immediate term to put in there? If you go, shoot, I don't have time to put in that sum, I don't know what. It's a delay of 2. That should be clean. That should now be z to the minus 2 y of z. And what do we have? Now we have this plus m equal 1 to 2 y of minus m z to the m minus 2. Or what's z? Scaling y of minus 1. That's minus 1 plus y of minus 2. There's now the two terms that have slid over. And what does this one get scaled by? Z to the 2 minus 2, or 1. So now that's our expression. We've delayed the one that's kind of the closest to us with this z to the minus 1, and the last one just comes in as a constant. That's property 3 of z transforms. Property 4, scaling in the z-plane. This is similar to how you might scale a waveform with an exponential. Like if you had f of t was a cosine, and then you said, oh, I want to scale that with an e to the minus 2t, you had a Laplace transform property that would allow you to change your transform for little f of t into something that allowed you to obtain the the Laplace transform of e to the minus 2t f of t. This r to the minus n is like a scaling, exponential scaling. R to the minus n, that just says, oh, put the r in the denominator, so you could think of this as 1 over r to the n. If you now sort of see what's happening, let's say f of n was, I don't know, let's say it's 1/2. Then if little r is 4, do you see that inside you have not 1/2 to the n, but you have 1/2 to the n divided by 4 to the n, so you really have 1/8 to the n. Do you see how you've now collapsed it down more quickly? Well, maybe that's too much conversation and hand waving. Let's just put in some expressions. Suppose f of n was some a1 to the n. a1 think of as some number. And if you want it to be exponentially damped, little a sub 1 is something smaller than 1. And let's say this is for n greater than or equal to 0. What's capital F of Z? What's the Z transform of A1 to the N? Because you can find the common ratio, and now you can write that down. We could write that in terms of powers of Z by multiplying top and bottom by Z, or we could write this as Z over Z minus A sub 1. That's the Z transform of little f of n. Now suppose that somebody gave you a little g of n and said, oh, this is actually f of n divided by r to the n. Or this is now r to the minus n f of n. And that fits right in with our fourth property. This is now what we're taking the Z transform of. How do we... Now what we do is anywhere that we had a Z in our transform expression, we replace it with RZ. We now simply need to find what is R. Well, in this case, it is R, so that this now says that we have capital G of Z is now f of RZ. Or everywhere we had an R, we would replace it, everywhere we had a Z, we would replace it with RZ. Or we now have RZ over RZ minus A1. Or that's Z over Z minus A1 over R, if we factor down an R from top and bottom. And if little r was 4, and A1 was 1/2, now you see that, oh, that's now has a pole at 1/8, which is much faster than what it was when A1 was just by itself at 1/2. Or you might just say, let's consider an example where you might let little A1 be 1/2 and R equal 4. Just to give yourself something to do tonight to see if that makes sense. What happens when you now do this scaling in the z-plane? You've essentially scaled z by a factor r. And what does that look like in the time domain? That now has influenced the exponential behavior in the time domain. One more property, final value theorem. And why do we want this? Well, this now allows us to maybe find the final value in the time domain without having to do all the inverse Z transforming. We can simply look at a limiting expression. Suppose we now have capital F of Z, we have that transform, and we're saying it converges for magnitude of Z bigger than 1. Do you see what that means? Where's the region of convergence? Now the region of convergence needs to include everything outside of Z equal to 1. So F of Z converges for this situation, which means it could converge from Z equal to 1/2 on out, and it would meet this assumption or this condition in this theorem. We just need capital F of Z to converge for all values of Z beyond 1. So the region of convergence includes all of the z-plane beyond z equal to 1. And we want all the poles of f of z when scaled by z minus 1, or by this factor z minus 1, are inside the unit circle. Then we can apply this theorem. So this really says we could actually have a transform expression, capital F of z, with one pole at z equal to 1, because it's going to get canceled by that z minus 1 factor. We now multiply capital F of z by z minus 1 and look at the limit as z goes to 1. And that's going to give us the time domain behavior of our sequence as the time marches off to infinity. Just like similar to the final value theorem in the continuous time setting. We let s go to 0. Now s going to 0 is similar in terms of location in the complex planes as z going to 1 in the z-plane. Did I see a question?
Yeah, so I guess going back to the scaling in the z-plane, if that's okay. So when you say that the z transform of f of n over Rn equals f of r times c, is it f of r to the n times c, or?
So now there's a question back on an earlier property. The question is here in the scaling property, and now the question concerns the scaling. If you know the z transform of little f of n, little f of n is our time domain sequence. We know what its z transform is. It's capital F of z. Now, if you wanted to find the z transform of a different sequence, and that sequence is different very particularly from f of n, it's just r to the minus n times f of n. So you plug in the appropriate n and you weight f of n by r to the minus n. That's in the time domain. Then in order to obtain the z transform of this new expression, this is now our g of n. G of z is going to be capital F of z with z's everywhere replaced with little r z. So we're scaling the original z. That's the reason for the title on that property, scaling in the z-plane. We're scaling the z variable in the original transform expression by little r. I'm not sure if that helps, but you might just go home and look at it. I would suggest that you work a few of these examples that I've put in the cloud. You can go access those in the cloud now after class. Everything's in the cloud these days. So you have a cloud, you can pull it out of the cloud and work it. The final value theorem makes it easier, or maybe cleaner or quicker, to find a limiting value of your sequence in the time domain. Let's now talk about frequency response in a discrete time setting. And what I want to do, and maybe what we will get to today, looking at the time, is let's try to put our mind back into what frequency response is in the analog version or in a continuous time setting. Or I'm really asking you, how will a sinusoid be filtered by a low-pass filter? That's the question to begin with, to get us thinking. How will a sinusoid be filtered by a low-pass filter? How would you answer that?
Only sinusoids with a frequency that are below whatever the
filter threshold is that we pass through?
Okay, so the answer, I was looking for something not as verbose, but your answer is correct. I was thinking you would just say, it depends. That's the short answer. But the long answer is consistent with what was just stated, and that is, what's my cutoff frequency, or what's my pass band of the low-pass filter? I'm only going to be favoring sinusoids that are within that bandwidth, and I'm going to be attenuating sinusoids that are outside that bandwidth. This is not an ideal low-pass filter. In an ideal case, you would pass everything nicely up to the cutoff frequency, and anything beyond the cutoff frequency you would just be throwing it away. Now we're going to talk about a first order low pass, and that's not going to be as clean as an ideal low pass filter. But may I just abbreviate that response and say it depends? It depends on the frequency of your input sinusoid and the cutoff frequency of your low-pass filter. That's why it depends. When somebody says, how will a sinusoid be filtered? I don't know. Depends on your filter cutoff frequency and the sinusoid you're exciting your filter with. Here's a low-pass filter, and this you should be able to draw immediately. On your next interview, if they ask you, design or draw me, sketch me a low-pass filter, you can say, oh, okay. You might sort of act like you're a little bit thinking so that it appears that, boy, yeah, they know their stuff. But you should just be able to write this down in your sleep. You have a resistor and a capacitor, and you're exciting the two of those with your input, that's V sub I, and you're measuring the voltage across your capacitor. It's first order. Why is it first order? We have one energy storage device, and that's our capacitor. And now the interviewer says, well, derive the transfer function for that low-pass filter. You think you gotten away from or answered my entire set of questions? No, it's not gonna be that easy. Yes, you can sketch the filter, but now give me the transfer function associated with that filter. And now you go, okay. So you write this down and you go, what's the impedance of my resistor? That's R. What's my impedance of a capacitor? You'll have to remember that. That's 1 over SC. What's the impedance of an inductor? SL. You don't need it here, but you might in the next question that the interviewer asks. Maybe he'll give you or she'll give you a second order circuit because they see on your transcript you've taken 320. And they go, okay, you can handle this. Give me a second order filter. Now what do we do? Now, as you're drawing this down and writing in these impedances, your mind is going, right? It's clicking, clicking, clicking. It's saying, okay, now how am I going to analyze this? How do I find the transfer function? What are some ways you could analyze this? There are many ways to analyze this. One would be, I've kind of forgot. Let me do a KVL equation. You could write a mesh equation, and then you could say, okay, I have the current through that series circuit. I'm going to multiply that current by the impedance across that, or the impedance of the capacitor to give me the voltage across that capacitor, and I'll be done. Or somebody might go, oh, that's just a voltage divider, where you have this impedance and that impedance to work with. It's really any way you want as long as it's correct, right? And two that jump out at us are KVL or voltage divider. Suppose we did the voltage divider. that now says that that output voltage, V sub 0, is really only a portion. It's a divided amount from the overall input voltage, V sub I. And how is it divided? Relative to these impedances. I'm seeing 1 over SC over the total impedance, R plus 1 over SC. That now, in square brackets, is the transfer function. And you now have ratios of ratios. You're going, maybe I should clean that up a little bit. That's not so difficult because you could get a common denominator in the numerator and denominator, or you could multiply top and bottom by 1, where 1 is SC, and you now end up with your transfer function, capital H of S, is 1 over SC, well, maybe I should write it in the way that you're normally seeing it, SRC, or RCS, however you want to, plus 1. And what is this RC? What have you referred to that before as? RC. That's my RC blank constant, time constant. So this RC is your time constant tau of the filter. Suppose now your interviewer says, she goes, well, create a 100 hertz low-pass filter, or a low-pass filter with a bandwidth of about 100 hertz. I was ready to shake hands and leave this interview. Just keeps going and going. How are we going to do this? Now what? It's going to depend on R and C, isn't it? And how do we translate this 100 hertz into, what is S? So S is a reciprocal of time, right? Tau RC is a time. We said time constant. So that must be in seconds, let's say. S must be something per second because we need that to be dimensionless. And we know that radians are dimensionless. So S is radians per second. All right. So now we know that F sub C, our cutoff frequency in hertz, is 100. How do we translate that into radians per second? That we have to go to this bakery and get some pi. 2 pi F, right? So now we have 2 pi. Are we going to celebrate Pi Day in here this semester? I don't know if we're going to have class. It's probably spring break. That typically is what happens. So you can enjoy Pi Day over spring break. But now we have 2 of them. 2 pi times F sub C. Obviously, it's a little past dinner time, maybe. I can't think about that. We're 2 pi. So now we have 2 pi times 100, or 200 pi, and the reason I said about 100, I want to just round that pi to 3. So that now we're going to say, okay, we have a bandwidth of 600 radians per second. That approximation symbol is taking account of our about 100. All right, so now we have omega c equal to 600. What's our denominator in this filter now? We now have an omega c, we have an SRC. What? Oh, man. How do we put these together? We have our denominator as SRC plus 1. Or we could, see, you're buying yourself time in this interview. You're just writing things down. And that gives you time to sort of think about what you need to answer this. You now have, oh, that's tau S plus 1. But I know my denominator will give me poles. Oh, yeah, and a pole will correspond to maybe a break frequency, and it'll allow my magnitude response to be going down. That's going to give me my bandwidth that I want. So now I say, okay, I now have tau S plus 1 equal to 0, or S, the value of S that causes that to vanish is my pole, because it's in the denominator of my transfer function. I solve that tau S plus 1 for S, and I end up with S is equal to minus 1 over tau. Oh. And I said that S needed to be radians per second. That's now my frequency. That's where my pole is in this low-pass filter. It's at S equal to minus 600. That's now my denominator, so that now if I needed to, somebody could say, well, what's your time constant now? Well, now I can just compare constants or variables in that expression. 1 over tau is 600, or tau is 1 over 600. You're buying time. You're buying time, remember? So this is now 1 over 2 times 3, because you forgot your... Oh, do you have a calculator I can borrow? That might be a little embarrassing in the interview. So you just keep going, right? Then you go, oh, man. Oh, but I remember what 1/3 is. 1/3 is 0.333, and I'm dividing that by 2. Feeling a little bit better. So that now tau, your time constant, is 0.16, let's say 7, or let's put another significant figure in there, times 10 to the minus 2 seconds. Or tau is 0.001667 seconds, or 1.667 milliseconds. So that our transfer function, h of s, is 1 over tau, 0.00167 s plus 1. That's now a low-pass filter with a bandwidth of about 100 hertz. What's the DC gain of that transfer function or of that filter? It's 1, isn't it? We evaluate h of s at DC. DC is when s is equal to 0. H of 0 is 1. What does that tell us, a DC gain of 1? Does that tell us anything? What if I put in a sinusoid with a frequency of 0.2 hertz to that low-pass filter? What can you tell me about the magnitude of that sinusoid at the output? What's the frequency of the output? It's the same. You shake that filter, everywhere in that filter it's going to shake with that frequency. You now have an output of 0.2 hertz. What's its magnitude compared to the magnitude of the input? It's the same because you have a DC gain of 1. It's maybe a little less than 1, but now at low frequencies you're passing those sinusoids with their magnitude pretty much unchanged. So now how do we sort of verify this behavior to our interviewer? Now they're saying, okay, you've given me a transfer function. Can you show me, can you verify, can you validate that that in fact is a low-pass filter in the S domain? What do we have? Well, now we have 1 over tau S plus 1. But tau was 1 over 600. This is now S over 600 plus 1. And you're looking at the clock and you go, oh, I've got 40 more minutes in this interview. So now you go, oh, this is a particular form. What form is this in? This has this is in a standard transfer function form. What is that form called? We're getting there. We're not yet to the pole zero form. The pole zero form is where we can explicitly see the pole, which we can kind of do here because it's first order. But this one, I had tau S plus 1. What was tau? Time constant. This is the time constant form, where my time constant is 1 over 600. That scales S. So this is now the time constant form. And when do you like a transfer function in time constant form? When you need to sketch that Bode plot. So this is now the form that you want it in to sketch the Bode plot. But you could also be thinking, you know what, I want to know where my poles and zeros are because that will allow me to identify on my frequency axis when I am sketching this Bode plot where things are happening. Now to put this into pole zero form, we need to make sure that we have all of our factors, our pole factors and our zero factors, such that we can explicitly see where those poles and zeros are. We can produce that here. Boy, 1 is very useful, isn't it? We're using 1 all the time. Let's multiply this by 1, 600 over 600, and now we have 600 over S plus 600. This is now in pole zero form. And that might be useful if we wanted to draw our poles and zeros in the S-plane to produce a pole zero diagram. What's the DC gain of this transfer function in pole zero form? It better be the same. We better not have changed this transfer function by moving it around between time constant form and pole zero form. They should be equivalent. It's just they help us see things differently for different situations. The DC gain here is again 1. We plug in S equal to 0, we get 600 over 600, that's 1. What's the Bodie plot look like? We know that the DC gain is 1. You heard me say earlier, about 2 minutes ago, we had 40 minutes left. I wasn't joking. We have that much time. We have 38 minutes left in this lecture. So if you're sleeping, wake up! If you're at home sleeping, nobody in class is sleeping. Everybody here is on the edge of their seats, trying to race out the door is what it is. But here is our Bodie plot. Now figure out how to label that a little bit better between now and Monday, and we'll pick up at this point. But I'm hoping you're starting to remember what's going to happen when we excite this with sinusoids. If they're on that flat bar of magnitude 0 dB, which is a gain of 1, then we're passing those and we're not favoring the sinusoids beyond that break. We'll pick up there on Monday.